This week we will look how we can apply our knowledge in practice. If we scale up from a laboratory scale to an industrial scale, we see that heat transfer becomes more difficult. One of the reasons is that the surface area for heat transfer becomes smaller in comparison to the volume. So the ratio of the heat exchanging surface to the volume is an important parameter. Many large animals, like elephants who live in warm areas, do not cool down fast because the surface to volume ratio is low in comparison to the one of a small animal like a mouse. However, elephants have different ways to compensate this. For example, they have big ears to increase their surface area without increasing their volume. Take your own body. We produce heat in our body and lose it through our skin. Roughly you can say that the ratio of surface area of the skin and the volume of our body is the parameter which determines the speed of cooling. A baby where the ratio is high cools faster than an adult. That's one of the reasons that babies who born too early have to stay in an incubator to keep their body temperature on 37 degrees C. To give you a feeling, I take a sphere and a cube, and the ratio of surface area over the volume of the sphere becomes 6 over d, and for a cube this becomes 6 over L. In both cases the volume increases faster than the surface area, which means that it becomes more difficult to cool down or to heat up the sphere or the cube. In industry it is quite similar. A lot of chemicals are produced in reactors where heat is produced. If heat is released during the process, it's necessary to cool down the reactor for safety reasons. Often the surface area is not sufficient to cool the process, and heat exchanger tubes are used in the reactor. Another way to heat or cool fluids is an external heat exchanger, which contains a large surface area to exchange heat, and this can be tubes, plates or more fin-like structures. You can also see them in many houses. With the knowledge you learned in the previous week, we will design a simple heat exchanger. It gives you a feeling which parameters are relevant, but also that basic knowledge of transport phenomena can be used in practice. Consider the sketch of this basic heat exchanger. It consists of two concentric tubes where a hot and a cold fluid flow through. Heat is exchanged between the hot fluid to the cooling fluid by means of the wall between the two faces. A hot fluid enters the inner tube and is cooled by the cold fluid in the outer tube. The energy phi Q is transferred from the hot fluid to the cold fluid. As a result, the fluid in the outer tubes becomes warmer along the length of the tube. If we know three temperatures, for example the inlet temperature of the hot and the cold fluid, and the outlet temperature of the cooling fluid, we can calculate the temperature of the hot fluid. How can we obtain the outlet temperature? Any idea? Think about the thermal energy balance discussed earlier. Under steady state conditions, we can say that the amount of energy phi Q is transferred from the hot fluid to the cold fluid. Further, we assume that the temperature increase as a result of energy dissipation is small. The thermal balances of the cold and the hot fluid under steady state conditions become now the following. If the mass flow rates and the heat capacities are known, we can obtain phi Q from the thermal energy balance of the cold stream. Using this value of phi Q in the thermal balance of the hot fluid, we obtain the outlet temperature of the hot fluid. Okay, we know all the temperatures, but to design a basic heat exchanger we want to answer a question like, what's the length of the heat exchanger? To answer this question, we need to know how large the surface area is over which the heat is exchanged between the hot and the cold fluid. In this example, we know the inlet temperatures and the outlet temperatures of the involved fluid, and as a result we know how much energy phi Q is transferred from hot to the cold fluid. The total heat transferred from one side to the other side can be expressed by the amount of energy exchanged between the two fluids. So the amount of energy phi Q is the product of the overall heat transfer coefficient, U, the surface area, A, and the so-called logarithmic temperature difference, delta TLN. The overall heat transfer coefficient, U, covers the process from hot liquid to cold liquid and including the conduction through the wall. Its reciprocal value represents the sum of all the heat resistances involved in the heat transfer process. This means that it is the sum of the heat resistance at the side of the hot fluid, the conduction through the wall, and the side of the cold fluid. In practice, it is often difficult to determine all these resistances separately. For this reason, the value of the overall heat transfer coefficient, U, is often used. The surface area, A, is the total surface over which energy is exchanged. For a tube, this is the product of the perimeter and the length L. The delta TLN is a logarithmic average temperature difference between the hot and the cold fluid, which contains the difference between the inlet temperature and the outlet temperatures of the fluid. Theory shows that along the tube the temperature difference changes and that this can be derived that the logarithmic temperature difference describes this process well. Here we will not go into the derivation of delta TLN. Delta in represents the temperature difference between the hot and cold fluid at the inlet, and delta out represents the temperature difference between the hot and cold fluid at the outlet. Summarizing, we can say that with the thermal energy balances and the equation we describe the heat transfer process between the hot and the cold fluid. We are able to obtain the surface area and the length of the heat exchanger. As illustrated, there are two ways of operating such a heat exchanger. The fluid can flow co-currently or counter-currently. The question is, what's the most effective way of exchanging heat? Co-currently or counter-currently? To illustrate this, we take an example of heating up a vegetable oil stream from 10 till 50 degrees C with a water stream of 70 degrees C. The diameter of the inner tube is 25 millimeters. The overall heat transfer coefficient U is 1200 watts per meter per Kelvin. And the mass flow rates of oil and water are 0.1 and 0.2 kilograms per second respectively, while the heat capacities are 1700 and 4200 joules per kilogram per Kelvin. From the energy balance, we can calculate the outlet temperature of the water, which becomes 61.9 degrees Celsius. Subsequently, we calculate the logarithmic temperature difference for both situations. For the co-current flow, delta TLN becomes 29.7, and for counter-current flow, 33.4 degrees Celsius. The temperature difference immediately shows that the counter-current one is the more effective one than the co-current one. Finally, it shows that we need 388 meters to heat up the oil co-currently and 346 meters for counter-current flow. This is an example for one tube, but it illustrates how you can design the size of a heat exchanger with the knowledge you have learned in the last weeks. Good luck with the exercises and thanks for your attention.